Earth system or Earth system modeling. Okay, so then why this seminar? Why these topics? Because nowadays is very important to use the artificial intelligence for the Earth observation, for data processing, and for modeling, because nowadays we have a lot of technology dedicated for data collection, in particular for satellite, but not only. And we are able to collect a very huge quantity of data, and it's very important. It's I think mandatory to try to use an intelligent, a smart solution for understanding the real contents of this data. Sometimes it's a really really critical to know what is the real meanings of the data, what is the real composition of the data set, because of course the quantity of data is really huge. Machine learning, but generally speaking, the artificial intelligence can help us to try to investigate, to analyze the data. But of course, the key points is how to use these tools, how to training the neural network, and at the end, I think, but Peter help us. I hope that it's very important to be able to understand the results given by the artificial intelligence tools, because using the black box machine of the artificial intelligence, we obtain some results. Is maybe our goal to know, to be able to recognize if the results is a good result or not. Then I hope that we have time to discuss about that. So before to leave the floor to Gianpaolo, I would like to say thank you very much to Peter for your participation, and generally speaking, special thanks to the ECMWF for the participation in this master. So thanks to Gianpaolo that for a long time, this is the third year that he is involved in the master. We have a very strong collaboration with your center. It's a very important collaboration for us, and I hope that this collaboration is a very long collaboration also for the future. And so this is an occasion to talk about what you are doing about the Earth system modeling, and also what are I think the new challenge about this topic. Then I close my introduction. Thanks again for your participation, and I leave the floor to Gianpaolo for to give an introduction about Peter. Thank you again, Peter, for your participation.
Thank you, and thank you very much, Marco. So it's my pleasure to introduce Dr. Peter Dueben. So Peter is the head of the Earth System Modeling section at ECMWF. This is my head of section. That's the section where I work. And he's really the ideal speaker to talk about machine learning in Earth System Modeling, because he has been coordinating the machine learning strategy at ECMWF, how to prepare for the future in which machine learning will be used in a massive and pervasive way throughout our workflow. Peter has a PhD from the Max Planck Institute for Meteorology in Germany, and he has been also a postdoctoral research assistant at the Oxford University, where he has developed several applications of machine learning, also reduced precision computation to really speed up computation in Earth system modeling. So it's my great pleasure to give the floor to Peter for his seminar. And thank you very much, Peter, for being here.
Thank you very much for having me. Well, welcome to everyone. I can't really see you, but I assume that there are kind of a couple of people in the room. I'm going to talk and talk and talk. And if you have any questions, please interrupt me. It's much more useful than if we have discussions throughout the talk, then having it at the end, in particular because I understand that the audience here is kind of quite diverse with the background. So I'm sure there will be slides that will be more difficult for some than for others, and so on and so forth. So please ask any questions during the presentation. So I'm going to talk about machine learning for Earth system modeling, but before doing that, I just have my standard slide on what we do at the European Weather Center, the ECMWF. I just suspect that Gianpaolo already talked about this in the seminar yesterday, but still, we're basically a research center, but we really have an operational weather prediction component as well, in the sense that we really build those operational weather predictions for what we call the medium range. So that's a couple of days into the future. And to do this, we basically need global models, because for medium range, you definitely need global model integrations for the weather. And this basically means that we also have our own supercomputers, because to kind of run those model simulations, you actually need supercomputing facilities. And we also have our own forecast system, which is called the IFS, which is among the best weather prediction systems in the world for global applications, basically. So that's us. And we now, as you may know, we used to be in Reading for a long time, but now we also have the computer has moved to Bologna, and now actually also some of the offices have moved to Bonn. So we're now basically turning into a multi-site organization across Europe. And yeah, so basically it's very close to our hearts to build those weather predictions in principle. And just one slide of like how these weather predictions in principle look like. You basically see the workflow of numerical weather predictions on the bottom here. So every day we will get hundreds of millions of observations into the weather center. Of those hundreds of millions of observations, we will basically pick tens of millions of observations. And then we're going to perform the process called data assimilation, where we basically have our observations and we have the forecast simulations from the day before, or from the forecast before the current forecast. And we bring the two information sources together basically to generate initial conditions. So we basically merge observations and the model trajectories to generate initial conditions. And then we run a forecast model, the numerical weather forecast, that basically looks something like 15 days into the future. And it typically generates a lot of output data that is then post-processed and disseminated in the last step, basically. And all of this needs to be done within a couple of hours. So these kind of 4 steps really need to be performed within something like 3 hours. And also to do this, you basically need high performance computing and data processing infrastructure that are kind of quite significant. And just to give you an impression of how complex and how basically, well, interesting those models also are, I brought you kind of 3 visualization here of wind gusts at the surface. And if I now start the visualization, and I hope you see it kind of well in the virtual world on your end as well, but you basically see a lot of detail there. So this is really kind of a forecast field that provides you with a lot of information about the global forecasts. You see all those kind of nice things like the topography in the Alpine region here. You can also see leeways of islands, for example. So there's a lot of things happening in this simulation, and the simulation is basically like something like 1 billion degrees of freedom. So it's really, really a big computing simulation. And those models typically basically consist of fluid dynamical systems for the atmosphere and the ocean, but then there's also other physical representations of things like land surface that Gianpaolo is looking very much into, or things like sea ice, land ice, and all these kind of things. So it's basically a very complex system that is running on a daily basis, twice a day in our case, and really kind of requires a lot of supercomputing resources. So that's what we do in the standard world. So now the question is, to some extent, why did we actually start to look into machine learning for a system modeling principle? And this kind of is a trend that basically started in something like 2018, so like 5 years ago now. But not much earlier. And the question is like, why did we actually start to look into machine learning in the first place? One of the big reasons is, and Marco already mentioned this, the increase in data volume. So just to give you a couple of numbers, we basically have a couple of hundreds of petabytes of data at our center. So it's hundreds of thousands of disks full of weather data, if you want. And this data needs to be kind of digested one way or the other. And machine learning is kind of a good way to actually do this. And what you can see on the figure on the right here is basically a plot that is showing you the timeline on the x-axis here. And the y-axis is basically the sustained performance that we had on our supercomputers. And all the different columns in the plots are showing you the different supercomputers that we were working with at the time. And what you see is basically that there's a constant increase of supercomputing power over time. And it's kind of a linear increase, which basically translates into an exponential increase because this is a logarithmic plot. And this basically just says like there has been an enormous increase in compute power within our weather simulations in principle. But you can also see the blue line in here. And the blue line is actually the growth of the data archive that we had at the center. And it's also a linear line, which basically indicates an exponential growth. So we really have this exponential increase of the amount of data that we kind of work with every day. And this is basically asking really for machine learning applications to basically to be able to really extract all the information that is in this data and to kind of really use this data in the most optimal way. The second point is that there's also new computing hardware. So this is a slide that I stole from Thorsten Höffler from one of his presentations, and it's showing like a lot of different labels of companies that are actually producing hardware specifically for machine learning. So what this slide should basically tell you is that the machine learning, the hardware development for machine learning is really a multi-billion-dollar industry, and this is kind of dwarfing everything else at the moment in the high-performance computing market. So even if you're not interested in machine learning in general, you should still be interested in the way how you use this hardware for your applications, because the supercomputers of tomorrow, or actually already of today, are actually optimized for machine learning applications in principle. The third point is that there is a lot of software available. So even if you are not really used to work with machine learning in general, it's kind of quite easy to get into this. So it's kind of, you can basically build a Python model with 200 lines of code and use kind of one of those libraries for machine learning that are very powerful, and you can do a lot of things with it, which makes it very easy to actually get going in this field. So it's basically something that should also not be underestimated. If you want to do conventional climate modeling, you typically have to touch 100,000 Fortran lines of Fortran code, for example. If you want to do machine learning applications, you can probably get away with 1,000 lines of Python code. So that's something also very interesting. And then last but not least, obviously have been a lot of progress in terms of developments of machine learning tools. So we're talking about something like 100 papers per day coming out on machine learning and artificial intelligence. Not quite as many in Earth system modeling, but still there has been basically a lot of progress in how we build those tools and how those tools can also be customized to specific applications. So that's basically where we are. That was the motivation why we started to look into machine learning in the first place. And then the next question is, why should we actually look into machine learning specifically for Earth system modeling? So what's different in our application area, for example, than when you compare it to language processing or other things? First of all, what is machine learning? I think for this talk, we can safely assume that most of the things that I'm going to talk about is supervised machine learning. So it's literally just learning a mapping between inputs and outputs. So you just collect a huge amount of data from inputs and outputs, and you learn the mapping in between. And you can do this with random forest or whatever techniques. You can do this with deep learning. You can do this with regression techniques or whatnot. But basically, it's literally just learning this method. And that's kind of the boring part about it to some extent. It's just basically a mapping procedure that we're learning. So why would this be useful? The Earth system is quite a difficult candidate, and even though I've shown you these kind of massive simulations in the past, and I was proud of all these kind of local details that we show in the simulations, it's actually quite a tricky one for conventional modeling, in a sense that you have this kind of complexity of the Earth system with all those different components that need to be represented. You also have the resolution issue. So if you make global simulations, you basically end up with something like 10-kilometer grid spacing, which means that important processes like individual clouds are not really represented. And also you have this nonlinear character. So errors are going to grow exponentially in time, which is also never kind of a nice thing if you want to kind of build a numerical tool to represent all this. On the other hand, as I said before, we have this huge amount of data. So we have observations from all sorts of sources. We have model output data. We have reanalysis data. We have everything. So we have a lot of data, and we have a very complex system. And if you now put those two things together and you also kind of realize that machine learning really is nothing else than a mapping procedure that you learn, it's kind of quite obvious that you can do this mapping procedure in a lot of different ways in Earth system modeling. So there are actually also loads of different application areas where you can kind of just extract information from the data to learn something about the Earth system. So there are many application areas in principle where machine learning can be used for system sciences. So it's kind of quite an interesting field for machine learning if you have a lot of data and a lot of uncertainty as well for conventional models. I think there is something happening in the chat. I guess the recording can be shared. I don't know.
Slides can be
yes.
shared later on. Yeah.
Yeah,
Perfect.
no problem with me.
Yeah.
No problem at all. Okay. So, and there's also more to come in that sense, because we're currently engaging with a project called Destination Earth, which is kind of a very large European Union project. And there we're kind of building forecasts or models that are really up to 1 kilometer resolution in global model simulations, which is something kind of quite spectacular, for at least if you kind of know the domain in principle. So we have going to have these huge model simulations with a very, very high resolution. And then again, we're going to be dwarfed by all these kind of information that is coming out. So again, machine learning will probably play a very big role here. And then on the other hand, also, we're currently facing what we call the digital revolution of the Earth system sciences. And what this basically means is that the current way of building our models, like very large Fortran source codes, is not really sustainable in that sense. So we need to think about how to actually make our models fit for the next generation of supercomputers. And then again, machine learning can actually kind of be a very kind of important ingredient of this kind of digital revolution. So we also need to rethink basically how we build conventional models in the first place. And now coming back to this diversity of different application areas. So what you see here is basically, again, our workflow that we have in numerical weather predictions. And then I think 2 years ago or 3 years ago, I asked around at ECMWF who's actually interested in doing machine learning in different components. And I came up with this slide here, and you really don't need to look into all the details. But basically, each of those boxes is someone who basically said, like, okay, machine learning could be interested in this area of research one way or the other. And what you see is there a huge amount of different boxes. So which basically means machine learning is nothing that you'd only want to do in one component of the Earth system modeling. It's really something that you would basically want to understand and apply maybe in all the different components of it. So it's something that is kind of going across the different sections and groups and departments at ECMWF. And also what you should see is that the connectivity is between the different application areas and each of those boxes in the workflow. So again, also from the workflow perspective, you basically, it's not the one thing that you want to do. It's really something that a tool that you want to apply in very different ways in the Earth system science domain. And kind of, this is a bit of the phase one, as I call it, to basically explore the space, to really understand, like, what can we in principle do with machine learning that basically lasted from 2018 to something like 2021, to basically look at all these boxes and understand for which of those boxes do we actually get a benefit and for which of those boxes we don't really get a benefit. That was basically our task in the first phase of machine learning. And actually, this is, again, like a bit of an attempt to try to summarize what people have been doing with machine learning in the area. So you can use machine learning to some extent to improve our understanding of the Earth system. So for example, you can take different data sources, like different observation data sets, for example, and learn the mapping between one data set and the other to try to understand and combine the different data sources. You can do things like causal discovery, where we're basically trying to understand connectivity between different features of the Earth system. You can do things like uncertainty quantification and so on and so forth. So we can basically really try to understand, improve our understanding of the Earth system. The second part is that you can also try to basically speed up our simulations. So you can think about things like emulation, where you basically just replace a conventional component by a deep learning tool, because it's much cheaper in the implication once you apply it to a specific part of the model simulations. Or you can basically also use machine learning tools because they're really optimized for the hardware to be faster in general than the conventional tools. You can also do things like data compression and so on and so forth. So there are a lot of avenues where you can actually speed up the simulations. The next one is that you can also try to improve the models. So you can basically try to learn model components within this kind of big Earth system modeling from observations, for example. You can do things like bias corrections where you learn the error. You can do quality control of observations and so on and so forth. So you can also kind of stay more on the conventional model side, but improve the different components of it. And then finally, something which is also really interesting for machine learning is to combine different domains. So let's assume you have a health data set over London for the last 20 years, and you want to understand how it relates to weather impact. Then you can basically just take the health data set and the weather data set and learn the mapping in between, and you will understand a little bit more of like how the two are related. And this can be done even if you have no theory whatsoever about how they are related. You can just learn the connectivities between the different domains. And that's also something very interesting where a lot of people are kind of looking into how to relate, for example, pollution data to weather forecasts and so on and so forth. So that's kind of the overall 30,000 feet summary of what people are doing in the field. There are also a couple of challenges, and I like to summarize the challenges basically with 3 different domains. So you have the weather and climate domain up here, you have the machine learning domain down here, and you high performance computing domain down here. And there are basically the 3 communities that need to work together to actually make the most out of machine learning in weather and climate. And there are challenges. One of them is basically that you have different philosophies in the weather and climate domain and the machine learning domain. So weather and climate really tries to understand everything in terms of the physical consistency and physical reasoning. And machine learning tries to basically build a tool that is working well. And there's often a different mindset in the 2 communities that needs to be overcome, but also in terms of the tool sets. So machine learning is based on Python and GPUs, weather and climate modeling is based on CPUs and Fortran and so on and so forth. There are also difficulties often to actually kind of interchange tools between the communities. Again, a problem basically that standard machine learning tools often need to adapt it to actually work well in the weather and climate domain. So often we will actually need to learn how to kind of work with the standard tools from machine learning in our domain to make something useful. The integration is often difficult, and I will have a slide later on to show you how difficult it can actually be. So if you want to work with a machine learning tool in the weather and climate prediction, you have to really make sure that it's working well and not just working most of the time, for example. And reliability is something very difficult if you have a system that you learn as a black box and you don't really have physical information about what the machine learning tool is doing. Then the scaling up to the petaflops. So most of the really big machine learning applications tend to kind of work with extreme computing sizes in terms of like what they actually do. And at the moment, we can't do this yet. We're still learning how to actually kind of use our model framework and kind of data framework on like large scale high performance computing systems. So that's something that we still need to learn. And then finally, the reliability is really an issue in a sense like, if you build a climate model from a machine learning tool, you can probably do this, but can you also trust it? These are questions that are kind of quite important and still, well, there's still a lot of debate about this. One way to actually get reliability into the mix is also to basically build on what we call physics-informed machine learning. So the idea here is, and there are different names for this. You can call it trustworthy AI or explainable AI or physics-informed machine learning, or there was something else I forgot. So basically a lot of different words for a very similar thing. And the idea is here that you kind of don't learn machine learning as a black box, but you just try to understand, first of all, what the machine learning tool is doing. And also you try to kind of project physical knowledge into the mix there. And as you do this, you basically learn to trust your application more. And it's also easier to get domain scientists involved because they want to understand what the tool is doing to actually trust it. And you can do this with several different ways. And I have the slide here basically because this is also something that is a hot topic and where a lot of people are looking into at the moment. So you can, for example, try to formulate your machine learning problem in a way that is actually more physical. So for example, conserving properties, you can basically ensure by kind of changing the way how you phrase your problem. You can also change the architectures of machine learning tools, in particular if you have deep learning and neural networks. You can close budgets for output variables, like artificially to some extent. You can also incorporate physical constraints into the loss function that you're training for. You can solve different equations. For example, there's a method called PIN, physics-informed neural networks, where you can literally just solve the equations using deep learning and so on and so forth. So there are different ways how to do it. And there's also different ways how to evaluate how well this actually reproduces the physical consistency. So you can also think about, for example, specific use cases for weather regimes, and you can just take a domain scientist and try to kind of look with him at the solutions and try to understand whether everything is consistent. You can perform sensitivity tests, for example, with a machine learning tool to understand whether the sensitivity is actually physical. And you see what you want to see in principle. If you, for example, warm up the planet, does the machine learning model is the response of the machine learning model is consistent, and so on and so forth. And then also you can test physical reasoning as well, for example, by looking into extreme events and basically cases that are outside of the normal distribution. However, the elephant in the room is to some extent that this is kind of quite tricky thing. So even though a lot of people are looking into physical consistency here, a lot of the approaches are actually not really generic in a sense that they actually solve the holistic picture of physically informed solutions. It's more like that someone has a good approach how to increase physical consistency, but in the end, you often still left with a black box tool in the end. And also there's a big of a trade-off between understanding and scalability sometimes. So you can build very, very nice physically consistent tools, but sometimes it's just better to throw a huge amount of data and compute power onto a problem with deep learning. And it's often kind of, there's often a trade-off between scalability and consistency. Okay, another thing, whoops, what people are looking into is also like how to combine, if you want, important physical features with the deep learning tools that you develop. And I just brought you one example here, which is coming from the scale interactions that we have in numerical weather predictions. So on the left side, you see basically a plot that is showing you how on the x-axis the important features that we need to represent in weather models are basically spread over 9 orders of magnitudes in space, and on the y-axis you have 10 orders of magnitude in time that are basically important for those features. This basically means that if you have microphysics in the cloud and the clouds develop basically on the microphysics side, so it's really, really very small scales, but then you build droplets and then kind of you build clouds. The clouds are bigger than scale. And then you kind of form thunderstorms that can be the size of a kilometer, for example, and those thunderstorms will then interact with the energy cycle that will then basically scale up towards hundreds of kilometers and interactions with jet streams and so on and so forth. So basically, everything, all the different scales in the system are really linked to each other. And if you want to build a good machine learning tool, you should also represent this kind of scale interactions. But you can do this. So you can basically use things like, for example, those encoding decoding networks. So this is a neural network where you have a high fidelity input, like a high resolution input on the left and a high fidelity output on the right. But you basically reduce the number of degrees of freedoms as you kind of increase in the depth of the neural network. And then you increase it again. So you should be able to actually represent something like a scale interactions using those tools. And there are a couple of good examples where you do this. Here's one example, for example, where we use represents the scale interactions in time for precipitation predictions by using so this encoding and decoding networks, but also other tools from language processing like activation layers. And you can try to basically represent those scale interactions quite well using the architecture that you have in the neural network. And that's also a very interesting research field at the moment. However, there's actually, again, an elephant in the room. So if you do this, it's fine, and you're going to get something going, and you're going to get interesting results in a sense like, okay, this network is better for scale interactions. But you will not be able to build a theory for this. So it's not that you can actually really build a theory for the scale interactions in turbulent flows, for example, based on different architectures that you've tried. So it's a lot of, well, a gray space again, in a sense that we all really have to kind of try to understand the basics of these representations by a lot of trial and error testing, because we don't have a theory for it. Okay, are there any questions so far?
Looking at the audience, would you like to ask questions now to Peter, some of you?
Okay, so I'll just go in, but please interrupt whenever there's one, as I said before. So just giving you a couple of examples, like how we are using, or how we are exploring machine learning at ECMWF and also at the wider area of basically Earth system modeling right now on the next couple of slides. So the first one is that we use so-called generative adversarial networks. And now I need a hint. Who in the audience knows general adversarial networks? Is there anyone? Or does everyone knows them? And I don't know exactly about the background. Silence. Okay, so I just assume you don't know them. It's fine for me. So basically, the idea of these general adversarial networks is that you want to generate pictures of celebrities, for example, and then you take a database of 50,000 celebrities, and you have basically some sort of information about them. For example, this one has brown hair, and this one has blonde hair, and this one is tall, and this one is small. And then I'm learning a deep learning tool that is basically generating faces of celebrities just based on random information and the features that I want to see. So I could, for example, say I want to have a reasonable picture of a celebrity which is blonde and large, like blonde and tall, and I want to generate 10,000 of them, and I will get 10,000 of those pictures. How does it work? You have a so-called generative adversarial network step that is depicted on the left here. So the idea is that you have one you have real samples of celebrities, and you have a deep learning tool that is basically generating new samples of celebrities that could be looking reasonable based on a random noise as input. And then you have a second deep learning tool, a so-called discriminator, that is trying to distinguish between those samples that come from the real one and those samples that come from the generator. And by doing this, you can basically, the discriminator is basically trying to understand which one are the real samples, and if it's getting better, then it will basically penalize the generator by basically saying, like, I know you, what you're doing, and the generator is trying to fool the discriminator. And in the end, you're building a tool that is actually very good in building those celebrity faces just out of noise. And that's interesting because we also want to do something similar in weather and climate predictions. So what brought you here is an example where we take model output data for precipitation over the UK at 10-kilometer resolution. And we also have precipitation fields from observations at 1-kilometer resolution over the UK. And in an ideal world, we could basically learn the mapping from the coarse resolution output to the fine resolution observations, and we would improve our results. So we would actually increase the resolution of those tools. But if we do this, we will generate a lot of uncertainty and actually also model error. So we basically will not be able to generate like the perfect mapping here out of the box. And this is happening. So we also want to represent uncertainties. So what we do is we use this generative adversarial network and generate a number of different outcomes, how they could look like, that you see here. So this is not really a video, it's basically just a couple of samples of how this precipitation field look like. And then we kind of can get really a good understanding of the uncertainty that comes with the mapping itself. And that's something very powerful, actually, and that can also most likely be used in other application areas. So that's something very interesting for us that we will continue in the future. Another example is that you can also use tools from language processing. So there are tools that are called transformer networks. And what they are basically doing, they're coming from the area of language understanding. And if you have basically a sentence like the animal didn't cross the street because it was too tired, then a transformer would be a perfect tool to understand what the it is actually about. So it would basically go back and forth in this stream of data, and it would understand that it's probably the animal that is meant with it. So there are tools that are kind of really targeted on these kind of understanding relationships between different words and sentences. And what we've done now is we've basically tried to improve our ensemble predictions. So in ensemble predictions, we're performing model simulations with 50 ensemble members in parallel. And we try to kind of connect the information across those 50 simulations with each other using the transformer network. So we basically fooled the language processing tool by just assuming that the sentence world dimension is very similar to our ensemble dimensions. And then we basically build post-processing tools on top of this. So it's again of this kind of try to understand how to combine very sophisticated machine learning tools with our world of Earth system modeling. And we get good results in a sense that we can actually improve our ensemble predictions with this. So again, we're using this kind of encoding, decoding network structure. So we reduce the amount of degrees of freedoms and increase it again. And we use transformer networks to basically build the middle part of this so-called unit structure. And we are able to kind of quite significantly improve our outcomes that we get from our ensemble predictions by using this post-processing tool. So there are interesting ways of how to combine real world and machine learning. I'm running a little bit out of time, so I'm going to skip this one. We also did a lot of work by emulating model components. So you can just basically take a specific tool that is maybe based on conventional modeling, but too expensive to actually run operationally. And then you can try to mimic this tool and then put it into the operational predictions. And you often get kind of almost the same quality of results, but the tool is much cheaper. So there are things that we can potentially gain here from so-called emulation as well. Okay, so now this was the first phase of the model development, so of machine learning and weather and climate modeling. And the second phase is basically now ongoing. So I said it started last year and it's kind of still going to take us for quite a while. And basically this is about now operationalizing those tools. So far, most of the tools have been on a research level, but we really want to use them in operations. And again, there's an elephant in the room, which is so far we don't really have many machine learning tools that actually made the step into operational weather prediction. So we really need to focus on this more in the future and kind of look into things. And it's actually quite tricky to kind of push models into operations predictions. And I'm going to give you one example here, which is a project where we looked into data assimilation. So in data assimilation, you bring the observations and the model trajectories together. They represent exactly the same weather phenomena. And then you can run the model for 12 hours. and diagnose the error that you have in your model directory in comparison to the observations. So you can actually measure the error. And once you have measured the error, you can actually try to predict the error with a deep learning tool. So you can just learn to predict a specific error for a specific weather situation. And that's quite a powerful thing in principle, because if you can learn the error of a conventional model, you can correct for it. So you can actually make a model that is has almost no error. So that's very interesting. We looked into this. We tried to learn the error from a direct comparison between the trajectory of the model and the observations, with the hope that you can then correct for the error in prediction systems. And that's something that actually worked quite well. So we have done some work with NVIDIA here, where we have on the left side the target error that we measure from data simulation, and on the right side you see the neural network prediction, and you see it's fairly similar in terms of the pattern. So actually surprisingly similar for us. You can see differences, no question, but it was kind of quite something to get this far, and we were really happy and said, like, perfect. So now let's put this into operations. But there's a big but, which is to generate this data here, we basically needed 12 years of data. So for the error prediction, and if we want to kind of learn the error for our current prediction system, we only have something like half a year of data. So deep learning only can work if you have enough data. So let's try it on the recent operational cycle. So now we have the same error pattern, the same plot on the left, but with the recent operational cycle in terms of errors. And we try to kind of get as good as possible with our deep learning tool on the right side. But now you can see, having less data, you can basically, the quality looks much worse, even with transfer learning applied. So there's a problem here. So even if you kind of have a good science project, it doesn't really mean that it translates and also into a nice operational tool in the end. Okay, I'm going to skip those slides here. And I just want to finish with one big thing, which is basically the question, like, how far can we go with machine learning? So I'm sure many of you have heard about the really recent examples about how good machine learning is with ChatGPT, for example, which is basically something that may or may not replace Google in a couple of weeks or month. So it's actually really high impact in the sense that machine learning tools can really make something conventional that we were working with on a daily basis maybe obsolete in a couple of weeks. So it's quite, there's a lot of examples where machine learning can really replace things and make them obsolete. Another example, for example, is where people have built in kind of an image model from machine learning, and then they were winning kind of quite prestigious art competitions, for example, just with a machine learning application. And that's, you can obviously say that's a bad thing, because we basically, well, we use the creativity from the artists to build a machine learning tool that then can beat the artists. It's highly questionable, but it's definitely something where well, machine learning is kind of threatening to some extent well, conventional tools. And you can ask the same question for weather and climate. So can we actually just remove everything that we've done before with weather and climate models and just use deep learning? And people are doing this in a sense that people are actually looking into the ability of machine learning to just kind of use very long data sets about the weather and climate trajectories, and then learning how to update this kind of the data set, update the state of the atmosphere from a couple of hours to the next. And once you've done this with a deep learning tool, you actually have built a weather forecast system. And there are people like Jensen Huang here, who is the CEO of NVIDIA, who is basically pushing this quite significantly in the sense that we really need to kind of learn how to use machine learning for weather and climate modeling and other fields, because this is going to be the future of high performance computing. So there's a lot of momentum there at the moment. And so the question is, can we replace conventional Earth system models by deep learning to some extent? And when will this happen? Will this happen at all? And there are a couple of papers coming out that came out recently, and there are a couple of applications. One of them is nowcasting, so the prediction of a couple of hours into the future. And I think this is a done deal, actually. Machine learning models will be better than conventional tools, just because they are so quick in the processing, and they also don't need to care about physical consistency with conservations if they just look a couple of hours into the future, that this is probably going to be the case. Another application is like very long-term predictions. And there it's actually a different story, because for long-term predictions like a season or multi-seasonal forecasts, it's more like a statistical model. You're not really predicting a specific weather situation over Torino. It's really that you're predicting a statistical correlation coefficient for a large-scale feature, for example. And it's a statistical model. So again, machine learning models are actually doing quite well if they're combined with conventional models in principle. So again, it's quite likely that these hybrid models are going to replace the conventional models at some point. Climate is a totally different story because machine learning models cannot extrapolate. So they don't really know how to deal with situations that they haven't seen in the training data set. But if you want to build a climate model, you actually need to do exactly that. So you basically run you progress a climate into the future, and you will see situations that you haven't seen before, like ice-free Arctic or something like this. So that's a big deal for a machine learning tool, and no one really has solved this yet. So conventional models are almost very likely to really still be on top of the other players for quite a while. But what about medium range weather predictions that we are interested in ECMWF? And again, people have really looked into these kind of global prediction systems, medium range weather predictions. So what you see on the left is a scorecard. So what you have here is different fields on the y-axis at different vertical levels. So there are a lot of, well, lines in here. It doesn't really matter. Don't look into the details, but just believe me that these are a lot of different forecast parameters that we are interested in principle. And on the x-axis, you have the timeline in days. So you have day 1 until day 10. And whenever this scorecard here is blue, means that Google has actually beaten our deterministic weather prediction system with their machine learning tool that it just published over Christmas this last year. So they're getting very, very good. This doesn't mean that we are going to be replaced at any time soon, but it does mean that those machine learning tools are actually kind of quite good. But the question is, like, how do these machine learning models actually work in a sense? Because they are really, really very different to our conventional models in principle. One of the things that is happening is that they're trained for what we call root mean square errors. So they basically try to reduce the error when they're running into the future. And as it turns out, actually, if you learn for those root mean square errors, the main effect that you get is that you smear out details. So you basically get results like this one, which is also from a recent paper, where on the left you have the truth. It's kind of a field, a global field that you have here that is progressing over time from top to bottom. And you see that it's basically consistent. So the 0 hours truth of the field is very much similar to the features that you see in the 72-hour forecasts. But if you build a machine learning model, this is not true anymore, because you basically try to reduce the root mean square error, which basically means that you kind of don't want to have sharp gradients in the solution in the end. And then you're losing a lot of features as you go forward in time. And this, after 72 hours, the forecast is quite smeared out in principle. So you're not really building like a great representation of the atmosphere. You're rather building kind of something like an interpolator that tries to please scores. And we still need to understand like what this actually means for the end user. So what does it mean for you guys if you open your weather app in 2 months from now? Would you actually be better off with kind of a smeared out prediction on the right, or would you be better, for example, with one with sharper gradients? That's an open question. And also those tools are using very large time steps. So it's kind of, they are very far away from a normal numerical dynamical, like a conventional numerical model in that sense. They violate all sorts of things like CFL conditions and whatnot. But they get away with it by basically kind of making sure that you have stability by just training for this, basically. So there are a lot of question marks of how useful those tools will eventually be. But they are definitely showing now to some extent, they have already shown that they will be useful. So whatever the world in 10 years will look like, I'm sure machine learning models will have their space next to conventional models, or however. So a lot of question marks. Can they extrapolate into unseen climates? Can they actually learn uncertainty, which is very important for medium range? Can we learn from observations as well? Can we fill the state vector in a sense that you will still probably need model simulations to generate training data and so on? Can they learn all the important processes? For example, if you have a 1 in 100 years event, for example, can you learn to represent those events from a 40-year data series, and so on and so forth? A lot of questions on the horizon. If you want us to help with those questions and you want to get involved, I can really highly recommend that you register for the MOOC that we are running at the moment. So we have a massive open online course that is currently running, but you can still register, no problem. Just go to this link down there, or just Google for MOOC for weather and climate, machine learning and weather and climate, and you will find it, I'm pretty sure. And this is basically an online course that you can take at your own speed. It will also stay there for a couple of years. So whenever you think it's going to be interesting, have a look at it. And that's it. My last slide is basically not really a summary of the talk, but it's also a bit of a, well, a teaser to some extent. So even if you don't really want to work with machine learning in a sense of replacing everything or something like this, you should still kind of think about the workflow, how you work with data in the future. And that's something that we as a domain will really have to work on more to kind of make it easy for everyone to work with machine learning tools. So just imagine if you basically have all the relevant data sets for system modeling, being observations, reanalysis, model output data, whatever, all available on a cloud, for example, somewhere in a supercomputer. And imagine that if you have kind of standard mapping tools between all the different data sets, how useful this would be for domain scientists that at the moment are really struggling to relate different observational data sets, for example, with each other, just because of the technical hurdles. And also the understanding of what's happening, I think that we can do a lot and kind of build more like automated tools of how to extract really information content from the data sets. And also regarding the interpretation of uncertainty, there's a lot to be done and so on and so forth. And if those tools are available in a scalable way and easy to use, everyone would be really kind of be able to extract much more information from our system data in principle, including everyone in the room if you would like to join us there. And that's all. Thank you very much.
Thank you. Thank you very much, Peter, for your really interesting presentation. Thank you. Thank you very much. I think we have a lot of questions, and then I don't know. So we can start question and answer session. If I can, I take the floor just for a couple of curiosity, but if other audience have some question, you are welcome. The first curiosity is about what you means regarding the transformer. So what is the improvement? What is the benefit, the real benefits of the transformer with respect to the traditional application of the machine learning? Because I think considering your model, it's very important to consider the evolution of the phenomena. So what is the real evolution of the phenomenon? So what is, considering your experience, the benefits?
Yeah, that's a very good question. And the problem there is that a lot is happening on the trial and error basis, in a sense. Like there have been quite a number of revolutions of how you do machine learning in the past, like convolutional neural networks were suddenly the thing, and then LSTMs were suddenly the thing, then attention mechanisms were the thing, then transformer, now it's diffusion, and so on and so forth. And each of those models are basically it's normally making things more complicated in a sense. So things get less intuitive and more complicated. And often, unfortunately, it is the case that you basically do trial and error testing and then you find out whether it's working well or not. That's kind of the ugly truth of machine learning, in a sense that it's really not so much physical reasoning, but really often just the pure trial and error testing. For the transformers, I think it's kind of intuitive in a sense that you can, in language processing, they are working very well by kind of connecting the different words and sentences. So you can basically learn connectivity between input variables that can be very far away from each other. So to some extent, the transformer can learn the optimal way how to combine information in a sequence. And I think that's the same in our case. So we can think about using transformer networks, for example, in the time dimension. And there are papers that show that it's actually useful in a sense that they can actually really pick the information where it's most relevant, in a sense that there's a specific weather situation like a thunderstorm that may be more influential happening a couple of days earlier, but the transformer could really pick out that one and just instead of just using the information from the last hour or so. And also in the ensemble dimension, it seems to be working well in the sense that the ensemble members can learn how they relate to each other by picking the optimal combination of the different ensemble members that are in this forecast.
And I have another. Thank you very much for the answer. I have another. So it's a sort of joke, a provocative question. How far is a Meteor chat GPT? Because so now the direction is more or less this one. So then Google is working about. I know that he's working about weather forecasting, just to give a more friendly interface. So when Do you think that it's possible to have a sort of method chat GPT or a sort of like friendly tools like this or not? Is a sort of dreams.
Yeah, this is a question that's very difficult to answer, actually, in the sense that we're literally talking about something that changed in the last couple of months. In the sense that Google published a paper, for example, in December at Christmas Eve, right? So it's basically something that we really still need to digest to some extent and try to learn what this actually means to us. Because as I also kind of phrased on the last slide, it's kind of quite different how those models work. I think it's a done deal that those models will have their place. So they will be good in predicting some things. For example, making really a 2,000 member ensemble is really simple with those models because they're that cheap in comparison. On the other hand, there are other things where they will not be so good. So, for example, if you take, I don't know, Hercule, for example, and exploding and volcano ash over Europe as an event that has never been before, those machine learning tools will be quite bad, whereas the conventional models will be able to represent those features. So it's kind of depends on the application area. So if I were to make a suggestion here, I would probably say that in the future there will be both worlds, basically. There will be some applications for conventional models and some applications for machine learning models. And also, don't forget that those machine learning models basically need conventional models to train from at the moment. So even if you want to basically build everything on machine learning, like Google does, they would still need a model to generate training data in the first place. So it's still a method of ChatGPT. Yes, why not? In a sense that Google. I mean, there will be applications where this is very useful, for example, and it's also much cheaper. So you can actually generate a forecast that would typically take in high-performance computer for conventional modeling. You can do the same similar forecasts with a single GPU, for example, in a similar time frame. So it's an interesting time at the moment.
Okay, maybe the next year we will see.
Yeah, exactly.
Okay.
That's a good idea. Yeah.
Thank you a lot. So I know if there are some audience. Yes, there is a question in the chat. I don't know if Peter, you want to read or I can read for you.
Yeah, there's a good question. How the models that predict error deal with overfitting, and if overfitting is something to worry about them. That is a very good question. I mean, to some extent, we know how to deal with overfitting, right? We basically know how to make sure that we have a test and training data set, so on and so forth, to basically make those typical tests to make sure that we don't overfit. And we follow them, and then we can be quite confident that we're not overfitting too much. On the other hand, obviously, if we don't have enough training data, this means that we will degrade the complexity of our machine learning solutions. And yeah, at some point, it's basically about the availability of enough training data. And then, as I showed you on the slides, this can be an issue, not so much if you want to build a general error correction term for like a standard tool that we're using in reanalysis data, for example, but really also if you kind of target operational cycles, and you will have a very short time slice that you can train from, and then overfitting will be a big deal. Also, building a model tool that can correct for the error doesn't mean that you actually want to use it in the end. So I can only recommend to talk to Gianpaolo after the seminar talk, because he can give you a rant of how difficult it is to kind of combine online error correction systems with operational weather predictions. Because once you do this, you actually correct for the error in operational systems. It's very difficult to then get rid of the bias correction tool again if you want to kind of improve your model setup into the future. So even if we would have a perfect error corrector, it doesn't mean that we could really use it straight away, because there are all sorts of problems and implications if you want to use it operationally.
Thank you very much to Alberto for the question. Other question for the audience? Or Gianpaolo, I don't know if you want to add something. That I know that we can spend a lot of time for about these topics.
I just a quick question on the speed of execution. So what I was mentioning to the student is that we need a supercomputer because we need to fit the critical path for forecast, and that's for us is faster than 1 hour. Could you comment on how fast are the machine learning? Because the training looks slow, but then the execution it's lightning fast, right? So that's
absolutely, exactly. So you will still need a supercomputer, but the supercomputer will mainly be used for the training, really. So for example, the Google paper, I think it's using something like 150 GPUs in parallel or something like this on the order. So this is already a high performance computing exercise, and it will run for a couple of days. But then the inference, so when you actually apply the machine learning tool, is really, really cheap because it's really optimized for reducing complexity. So therefore, I mean, the conventional model has 1 billion degrees of freedoms and needs to make a time step every couple of 100 seconds. The machine learning tool has 200,000 degrees of freedoms and needs to make one, and a time step is something like 6 hours or 12 hours or 24 hours or so. So we're talking about a factor of 10,000 or something like this in terms of the speed of the inference. So yes, it's that cheap.
That's really impressive in terms of matching performance at 10 times cheaper. So any question here from yes, there's one question. I pass you the microphone.
Thank you. Thank you, Peter, for the presentation. And just a curiosity from my side, because we face this machine learning development, fast transitions and improvement. But from your knowledge, based on your knowledge and point of view, what do you think could be a big transition point in terms of technologies in implementation? I mean, more related to input data or more related to performance of supercomputer or what? Yeah, I think we are going towards a world where machine learning will play a bigger role in weather and climate predictions, but I don't think that machine learning will ever be doable without conventional modeling as well. So I think we will have both at the same time coexisting. And the question is, where is going to be the equilibrium? Is it going to be closer to conventional modeling or closer to machine learning? And I don't know. I'm still scared, and not only in a sense that machine learning kind of may really be impactful, and that we, for example, at ECMWF would maybe have to kind of rethink how we do things, but also in a sense of like how we train people. For example, you guys in the audience here, you will soon maybe have the choice between working more with a million photon line code with a conventional model, where you have papers from the 60s that you basically read sometimes, or whether you want to kind of work on this very dynamic machine learning side with very small models and kind of a lot of progress happening and so on and so forth. And I guess a lot of people will tend more to the machine learning side, which basically means that we also need to think about how to kind of still keep up, if you want, the more conventional modeling side alive in terms of new people working on it and so on and so forth. So there is a bit of a, I mean, you mentioned like a transitioning point. I think we have reached this transitioning point to some extent, that the domain is going to shift further and further to the machine learning side. And we need to make sure that it's kind of still balanced in a way that it's also justifiable how much it is kind of going towards machine learning without losing track of the important work for the conventional side as well. Does it answer your question? Yeah, thank you. The second curiosity, the last one is provocative, of course, a little bit. From your point of view, how long do we need to wait for a very huge accuracy data and providing forecasting? I mean, just looking into this kind of trend of development, what do you think about it?
Oh, well, we have, I mean, we have data that is as good as it can be to some extent. I mean, we have, as a community, we have the reanalysis data, for example. So that's kind of a data set for the last 40 years that is consistent and really of very, very, very high quality. So I think in terms of data, we actually have a lot. We also have now weather forecasts in principle, like we have enough data to train all the machine learning models in the world. The question is a little bit more like, how will this data develop? And you can ask the same question for ChatGPT. So if you assume you're living in a world in the future where every content will be derived by ChatGPT, so whenever I want to write a love letter, I would just go to ChatGPT and just say what I want to have, and then I will get the love letter. But this does mean that there's not going to be better love letters in the future, right? It's basically going to store. And you can ask the same question with weather and climate data as well, right? I mean, if you want to kind of make progress, you basically need to, it's not enough to have a good data set in the first place. You also need to develop the data sets that you're training from. And I think their conventional models will always be the key part. And also with, for example, projects like Destination Earth, for example, we are entering a whole new realm where you basically go to 1 kilometer data globally that wasn't there before. So by those conventional model projects, you actually kind of achieve also by building kind of huge data sets that will be of huge value for future machine learning. So it's kind of a bit of a transition that needs to kind of continue in a sense. So we are starting from a very good baseline, actually. We have much better data sets than many other domains to start training from it. This is actually also one of the success stories why Google and others actually looked into this from the first place, because they saw that there's a lot of data that is interesting, but we will still need to kind of move the benchmark there and move the data quality.
Another question here.
Hi, thank you so much, Peter. And my question is, how do you address ethical concern related to the use of machine learning in climate forecasting, such as potential biases in data or time or some prediction of consequences that are really strong for a lot of population? I mean, maybe if these data are open to the population, can make faster migration and make, I don't know, some problems.
Yeah, it's a good question. There are kind of a couple of very nice papers on this. There's, for example, a group around Amy McGovern, where she's basically publishing papers on the topic of ethics of machine learning in weather and climate. And it's a topic that is really interesting to look into. I would argue that for most of the applications that you've seen on my slides so far, it wasn't a big topic, in a sense that if you just have weather forecast data that is kind of not discriminating against any area in the world or against any kind of, well, it's basically just physical data, and then ethics is not such a big deal. But it's getting there in a sense, like if you kind of really are serious about machine learning, you can also think about introducing observations, for example, from mobile data into the mix of the observations, but then you're straight away running into ethical problems there, because you may be able to actually identify what specific people are doing if you kind of take their observations. So there are things to be looked into, and people do in the domain. But so far, from my perspective, personally, I think we're kind of fairly safe still, because we're working mostly with kind of physical data that is coming from large-scale 10-kilometer type resolution levels. But there's more to be looked into in the future.
Great point on this of liability. Yeah.
Yep.
Any other questions here in the room? Or Peter?
I have a question from remote, if you hear me.
Oh,
Yeah,
yes.
we can hear you.
Okay. You were saying about climate science, machine learning in climate science, that we are currently having problems because of essentially the non-stationarity of the climate in this historical moment. So machine learning doesn't manage to infer because of the lack of data. No. Mm-hmm. I was wondering about applying machine learning instead in the climate modeling, but in the analysis of climate data and climate simulations that already exist, and even if in ECMWF, if you are applying in some way in this field.
Great question again. So yes, you can. If you don't trust your machine learning models in the future state, because you assume that your data set is changing and you don't know how, then it doesn't mean that you cannot apply machine learning together with climate model output, where you basically know how they evolve, and you can, for example, increase the statistics of climate models, for example, by using machine learning tools and so on and so forth. So yes, there's still application areas in climate modeling. We at ECMWF, we don't do too much climate modeling. So we do mostly, as I said, normally the core products of ECMWF is kind of medium range predictions up to seasonal. There's also the reanalysis part where it's interesting to use machine learning, but there's not too much climate modeling as such. But we're working together with, for example, the EC Earth Consortium, and they are doing climate modeling, and they are indeed projects where people are looking into how to increase statistics from existing climate simulations, for example, using machine learning tools. So there there are some interesting areas, but it's kind of, yeah, it's more like enhancing the information that you already get from us from climate simulations rather than making predictions that are just pure machine learning.
Okay, thank you.
Thank you very much. So, no more questions here in the room. What about online? Are there other questions online? Or otherwise, we can really thank you, Peter, for this really fantastic seminar. Very, very inspiring. Lots of questions, so that's always great. And I pass the word to Marco that I see is online. Whether you want
Yes.
to say a few words. And
Yes.
big thanks from me. Yeah.
Okay, so thank you very much for your presentation and also for, generally speaking, for the collaboration of the ECMWF in this master. I think that we have had a very nice discussion about the artificial intelligence and what is the possible future challenge about these topics. So thank you again to the participants for the question and the real enthusiastic participation. So thank you again, Peter, for your contribution. I hope to have the opportunity to organize another meeting, because I have seen that the topic is really hot for the PhD, for the students. Then we hope to organize another talks about these topics. Thank you again, and I wish a nice evening and a nice day. Thank you again.
Thank you for having me. Bye-bye.
Okay, see you the next time. Thank you. Thank you to the participants. And thank you, Gianpaolo, for the logistic and the organization in the room.
Pleasure. Thank you so much.
And thank you, Sophia. Bye-bye. Have a nice evening.
Bye, everyone.